Today we're going to learn about the third of our DC circuit quantities, resistance. In order to understand resistance, let's try to answer the question, why is a potential difference required throughout a circuit in order for charges to flow? Let's see if we can figure out why charges need a potential difference throughout the circuit in order to keep moving in the conductors of the circuit. I'm going to use an analogy with Hot Wheels cars. Now, you can see why we might think that if you just give a car a potential difference at the very beginning of its motion, the car will keep moving and it won't stop. That's what we expect from Newton's first law. But a circuit isn't like a smooth path like this. Conductors are actually more like this. They have little roadblocks to the flows of the charges through them, just like I've put little tape roadblocks on the track for this Hot Wheels car. So if I give it some potential energy at the beginning and let it go, it comes to a stop because it comes up against this roadblock right here. If I give it more potential energy so I can get past that roadblock, it stops at the next one. If I give it more potential energy there, it stops at the next one, and so forth. So I have to continuously give my car a potential difference in order for it to keep moving through all these little roadblocks. And the same kind of thing goes on in electric circuits, only the roadblocks are called resistance. As we have seen, it is the electric forces caused by the potential differences set up by the surface charges in our circuit that causes the charges to move through the circuit. And now we have an explanation for why you need to have a potential difference everywhere in the circuit. The potential differences give energy to the charges, but then they give up that energy when they collide with the particles of the conductor. Let's see if we can quantify this concept of resistance because different conductors will have different amounts of it. The resistance is defined as the ratio of the potential difference across the conductor to the current that is produced in the conductor. This is a definition. It is not a derived formula. Resistance is measured in a quantity called an ohm. So, if a potential difference of 1 volt produces a current of 1 amp through a conductor, then that conductor has a resistance of 1 ohm. Let's talk about the simulation lab that you did. In the lab, you use an ammeter to measure current. Now, in the simulation lab, the ammeter might have just been a device that you laid on top of one of the wires. But in a real ammeter, the current has to flow through the ammeter in order for it to detect how much current is flowing. So it is actually placed in the circuit itself. It becomes a part of the circuit. You also used a voltmeter in your lab to measure the potential difference. Voltmeters are always connected to 2 different points to measure the potential difference between those points. Typically, a voltmeter will have a black probe and a red probe. The black probe is attached to the initial point, and the red probe is attached to the final point that allows you to determine the potential difference from the black side to the red side. So, for example, if you connected the black probe of your voltmeter to the negative side of your battery and the red probe of your voltmeter to the positive side of a battery, you should get a positive potential difference because charges that are going through the battery are gaining potential energy, so they're gaining potential. On the other hand, if you connected the black probe of your voltmeter to the side of your electrical device that was closest to the positive side of your battery, say at point A in this picture, and you connected the red probe of your voltmeter to the other side of that device, as the charges flow through that device, they're giving up their potential energy. So they're giving up potential. So the potential difference there should be negative. If you have not completed the voltage versus current lab, please do so now, and then continue the video once you have it done. So if you did the lab correctly, or if you used the data that was provided to you, you should have seen that the voltage versus current graph was a straight line going through the origin. That means that voltage and current were proportional in this light bulb. The constant of proportionality was the resistance. And on this graph, the resistance would be the slope of the line. Because we found that voltage and current were proportional in our lab, we can state that our electrical device follows what's called Ohm's law. Ohm's law states that for many materials, resistance is constant. That is to say, voltage and current are proportional over a wide range of potential differences. Now, not everything follows Ohm's law. In fact, real light bulbs typically do not follow Ohm's law. They are said to be non-ohmic. They may have a graph that looks something like the graph on the bottom here. If your device follows Ohm's law, then as we have seen, you can just use the slope of the voltage versus current graph to find the resistance. Even if it doesn't follow Ohm's law, you can still use the information taken from the graph to find the resistance. One would just take the voltage at a particular point and divide it by the current there, because the definition of resistance is the ratio of voltage to current in that particular situation. In many electric circuits, you want to have a device that follows Ohm's law, so we'll use something called a resistor. A resistor has a known amount of resistance. The symbol for resistor is a zigzag line. That's really supposed to just represent a lot of wire for charges to flow through. The more wire you have, the more resistance you have, as we will see shortly. The resistance of a conductor depends principally on three things. The first is the cross-sectional area of the conductor. Consider conductors 1 and 2. Now, if I place a potential difference across 1 and it's the same potential difference across 2, it's like 2 has more paths for current to follow than 1 does because it has a wider area. Therefore, the resistance of conductor 2 would be less than the resistance of conductor 1. The next factor to consider would be the length of the conductor. Consider conductors 1 and 2 again. Conductor 2 has more resistance because there's a longer path that the charges have to get through. Think of having a longer track with a number of bumps on it, like with the Hot Wheels cars. Finally, the resistance of a conductor depends on what it's made out of. A conductor made out of gold will, all else being equal, have less resistance than a conductor made out of copper. One difference is that some materials have more free charges available to carry a current. Temperature also plays a role in the resistance of a conductor. We combine all three of these factors in a formula that defines a quantity called the resistivity of a given material. The formula is the resistance of a conductor is equal to its resistivity, abbreviated by the Greek letter rho, times the length of the conductor divided by the cross-sectional area of the conductor. The resistivity is a property of the material making up the conductor. The resistivity of a given material depends on the temperature. Most materials have less resistivity the lower the temperature.